Welcome to functional analysis. This is going to be perhaps 2 lectures on open mapping theorem. In functional analysis, the harmonic theorem, open mapping theorem, closed graph theorem, bounded inverse theorem, and uniform boundedness principle. These are essentially the pillars. Okay. And out of which harmonic theorem and open mapping theorem are the most difficult one. I had already released like 4 videos on harmonic theorem with all painful details included. So this time we are going to talk about open mapping theorem. As I said earlier, I am assuming you learn basic functional analysis, nonlinear space, etc. Okay, and later I may cover those materials, but for this particular thing I expect the prerequisites are met. Though I will briefly explain, because I find many students do not learn those things properly and they are even not taught most often. Okay, let's get going. So the reference is as usual our book on functional analysis, a 4th course. So what does open mapping theorem say? Let X, Y be Banach spaces, that is complete nonlinear spaces. Let T from X to Y be continuous and linear. Usually people say bounded linear. In functional analysis, that's a word most often used, but I prefer continuity so that it's easier. Okay, the most important thing is we assume T is onto. Extra hypothesis, T is onto. Then we want to say T from X to Y is an open map. I will explain in a minute what it means. If you had already learned metric space topology or topology in general, you know what this means, but we will quickly go through that. What does that mean? Suppose X and Y are topological spaces, or if you don't like them, metric spaces, and suppose F from X to Y is continuous, is just a map, not necessarily continuous. Right? Then we say F is open. F is open if for every open set U in X, F of U is open in Y. That means it maps open sets to open sets. Okay, this is the definition. So what does that mean? So if T is a continuous linear map from your Banach space X onto a Banach space Y, then it is open. See, these open mapping theorems are very important in analysis and topology also in general. Okay, at least 3 occasions you should be aware of. One is here in functional analysis. The other one is in complex analysis. There is also an open mapping theorem. If you have a non-constant horomorphic function on a connected open set, then it is an open map. Okay, third thing is in several variable calculus, where we proved inverse function theorem. The most difficult part of the inverse function theorem is the map under the stated condition is an open map. Okay, many times in no analysis book, etc., they bring it out, but my forthcoming book will show that. Okay, so in all these 3, they are important because this one allows us to define some kind of an isomorphism. Okay, isomorphism in general thing, we will come to it a little later. Okay, right. So let us just try to understand open maps. Let F be a map between, then if F is open, I want to say if and only if for every X in X and R positive, okay, there exists an epsilon positive so that b f of x epsilon is contained in f of b xr. There is nothing. Okay, it's very easy. Do not be intimidated, and I do not write like y and here x etc. because it's an open ball in y because fx lives in y. Therefore, the ball should be with respect to the metric. Similarly, I don't write dy dx. The context should make it clear because you and I are intelligent. Okay, right, right. So is this clear? Remember, this is open in x, right? So in particular, fx belong to f of bxr. Okay, then what do I, if I want to show this is open, okay, then this must be an interior point. Alright, so what I'm saying is there is an open ball centered at fx with the radius epsilon which is contained in that. Therefore, fx becomes an interior point. You understand that? We are not trying to prove this itself is open. We are only trying to prove only one point, namely fx is an interior point. Catch the subtlety? Okay. Okay, right. So this is very clear because one way, if that is if f is open, then this is true. Just now I explained, right? If f is open, this is an open set, therefore this must be an open set, therefore fx belong to that, therefore it must be. If this is an open set in a metric space, what does it mean? There is an open ball centered at this point which is contained in this. That's what we have claimed. Okay, right. Converse is also clear. Why? Suppose u in x is open, then to prove f of u is open in y, right? So let y belong to u, f of u. Then what should I show? I should show there exists an open set v so that y belong to this and v is contained in f of u. Because for every y I am showing, that means f of u is open. You understand that? If you want to call it Vy, then f of u becomes union of Vy as y varies over f of u. So union of open set, therefore this is open. Is that clear? Right. So I have to show. So let y belong to this. But y belong to f of u. What does it mean? There is an x in u so that f of x equal to y. Right? Okay. Now, since x is in u and u is open, that means there exists an r positive so that b x r is contained in u. Is that clear? Yes. But what do I know about that? Therefore, b of fxr is contained in f of u. Right? Right. Now, by hypothesis, there exists an epsilon positive so that b f of x epsilon is contained in f of b xr, that is contained in f of u, but this is just b y epsilon contained in f of u. Since y in f of u is arbitrary, this shows this f of u is open. So pause, review, proceed. So what we have done, we have reduced the characterization of open sets in the metric spaces in a very special way. We can do better. That is, if t, suppose x and y are just nonlinear spaces, not necessarily Banach spaces, and t x to y is a linear map, not again continuous, and not necessarily complete. Okay, then T is an open map if and only if. Okay, let me give a notation. Okay, by B of x I mean the open ball in B01 in x, and B of y similarly B of 0 1. Okay, if and only if, okay, there exists an epsilon positive such that epsilon times b of y is contained in t of bx. Again, do not be mystified, do not try to memorize. What does it mean? See, bx is open. I want to show t is open. Suppose if t is open, this is an open set. Notice that t is linear and 0 belongs to bx. Therefore, t of 0, namely that 0 belongs to by. And if I want to show this is an open set, 0 must be an interior point. What is the neighborhood of 0? The neighborhood of 0 is of the form b0 epsilon with respect to y, where 0 is in y. Okay, but this is nothing other than epsilon times by. I will come to it in a minute. Okay, please make sure you understand this. Okay, so before we go further in any nonlinear space, these are the things why I expect you to learn. Okay, bxr by definition is set of all, okay, let me write bar, set of all x in x, so that norm of x minus a is less than r. I claim this is nothing other than a plus r times bx, where bx is the open unit ball. Now what is r times bx? Remember, bx is a set of vectors, therefore this simply means r times each and every vector in bx, right? R times bx is nothing other than ru, where u is in bx. Okay, this is the basic observation, very trivial to prove, because if f is belong to that, then okay, then x minus a norm is less than r. That means x minus a belong to r times bx, right? R times bx is set of all x in capital X, so that norm x is less than r, right? Therefore, so if I write x minus a equal to some vector b is in r times bx, right? Then I can write it x minus a to r times a vector u, where u is b by r. Then norm of u will be less than or equal to 1, less than 1, strictly less than 1. Therefore, x equal to r ru, that means it belongs to a plus r times bx. Converse is also easy. The other, okay. Reverse inclusion, I leave it as an exercise. So again, pause, review, proceed. Now we are ready to prove what we wanted to do. What we wanted to show? We wanted to show tbx should contain y. Okay. One way is proved. If t is open, implies there exists epsilon positive, such that epsilon times by is contained in tbx, because this is open containing 0, therefore it should contain an neighborhood of 0, which is epsilon times by. Okay, now we want to prove the other one. Okay, right, let me just take a break. Hi, sorry, I have to attend to a call, that's why I took a break. So let's continue. Yeah, so let us assume t from x to y. These are all nonlinear spaces and linear map, and with the following property. Okay, well, there is an epsilon such that epsilon times by is contained in tbx. Then I want to prove t is open. Okay, so let u in x be open. Okay, let's talk to u. This is exactly similar to the way we worked out with the metric space. That's why I did a simple case so that you will follow this. That means again there exists x in u so that y equal to tx, right? And now x belong to u, u is open, that means there is r positive so that bxr is contained in u, right? Now let's try to understand what is bxr. We already know bxr is nothing other than x plus r times bx, right? Now if t is linear, right, you start with any vector here, it's of the form x times r times u, where u is in bx, right? Therefore, what will be t of that? Tx plus ru will be tx plus t of ru, but that is tx plus r times tu. But tu belongs to t of bx, right? Therefore, what we find is this belongs to tx plus r times tu, tx. Sorry, r times tbx, right? Therefore, t of bxr is contained in, just operate t on this, then you will know that is tx plus r times tbx. Yeah, so just pause, review, proceed, because these are the small things which you are never, just like that one writes, but we have to work carefully, because bxr is a set. When t operates on that, what happens? It's another set. That set is this. Now what is our assumption? There exists an epsilon positive, so that epsilon times by is contained in tbx. Therefore r times epsilon times by is contained in epsilon times tbx. So, r times tb. You follow that? Yeah. Therefore, what do I have? Therefore, tx plus r epsilon times by is contained in tx plus r tbx, but this is nothing other than t of bxr. And what is this? This is nothing other than open ball in y centered at tx of radius epsilon. Therefore, that is contained in tv of bxr. Right. So what have we shown now? So we have now notice that my tx is nothing other than y. Therefore, b y r epsilon is contained in t of bxr, but t of bxr is contained in t of u. Right. Therefore, we have shown, okay, any y in u, t of u is an interior point of t of u. That means t of u is open. Okay. So we have proved the following result. I'll just in summary, this is what you have proved. Notice that x and y are non-linear spaces. T from x to y is linear. I am not assuming continuity here. I am not assuming completeness here. Okay. Then T is open if and only if, okay, there is an epsilon positive, so that epsilon times by is contained in t of bx. You see that? We don't have to work with any open set u, and t of u is open. We reduce to something to t of bx. Right? That also what you have to show? 0 is an interior point of t of bx. Right? That is, we have to, t is open if and only if 0 in y, okay, is an interior point of tbx. Yeah, enjoy this. So you can see the beauty of mathematics, namely when you put some extra hypothesis, that is, if the structure is richer, okay, then you get beautiful results. See, when I have only two topological spaces, if I want to talk about a map from Pf from x to y is open, there is a definition. Okay, then if I have to prove a map is open, I have to check that. Whereas in the case of the vectors, the topological spaces become non-linear spaces and the map becomes a linear map, then we get a very easy way of checking whether the map is open or not. Namely, 0 must be an interior point of the image of the open ball, unit open ball in X. Enjoy this kind of mathematics. You will love to do that. Yeah? Okay, let's go back. Next, we want to show. So how do I going to prove that? So we are going to put the first step. Okay, now let's assume x and y are Banach spaces and t from x to y is continuous, linear and onto. You see that? Now hypothesis becomes more and more. Okay, so to prove t is open, what should I do? I have to show, look at tbx, then there is an epsilon, so that this contains this. Okay, that is 0 is an interior point tbx, right? Okay, so what we are going to first prove is that, look at tbx. Okay, it take its closure in y. Okay, we want to prove this contains an open ball b0 epsilon in y, of course, that is epsilon times by. So what we want to prove is tbx itself contains, but at present we are going to show the closure of tbx contains. Okay, right, please understand this kind of thing. So the proof involves various ideas. The first one is geometric ideas. About tbx closure, let me call it C. And second uses the so-called Baire's category theorem. I will simply say Baire's theorem. I don't like the word category. Okay. And third, again, the topology of balls. Topology or geometry of balls in a nonlinear space. Okay. Let's go slow one by one. The first geometric idea. Let C equal to tbx closure. We want to show what are the geometric properties. Notice that bx is convex. That means what? Whenever x and y are in bx, 1 minus t times x plus t times y is in bx for 0 less than or equal to t less than or equal to 1. Okay. Now notice that tbx is also convex. Why? Because tbx will be 1 minus t x plus t times t of y, where it takes two elements here. They are the forms of tx plus ty, where x and y. Maybe I should write x1. Maybe let me write u and v. U and v are in bx. Okay. Therefore, start with some y and z. Y is of the form tu for u in bx, and z is of the form tv for v in bx. Yeah. Therefore, I have to prove 1 minus t times y plus t times z belong to tbx. Okay, but that is nothing other than 1 minus t times y plus t times z is nothing other than 1 minus t times tu or tu and v, right? Yeah, plus t times tv. But remember, t is linear, therefore it is same as t of 1 minus t times u plus t times v because of linearity. And this belongs to bx because bx is convex. Right? Therefore, we have proved this belong to tbx. Therefore, tbx is convex. Right? Next, I want to say it is symmetric. tbx is symmetric. Why? What does it mean? That means whenever x belongs to tbx, then minus x also belongs to tbx. Sorry, y. Let us say y. Okay. Yeah. That is very clear, because if y belongs to tbx, so I wanted to say tbx is convex, therefore I should symmetric. That means whenever y belongs to tbx, I have to show minus y belong to tbx. Right? Since y belong to tbx, y is the one tx. Where is x? X is in bx. Now notice that minus x belong to bx. Why? because norm of x is same as norm of minus x. If this is less than 1, this is also less than 1, right? And since t is linear, therefore minus y is nothing other than t of minus x. Therefore that belongs to tbx. Therefore tbx is symmetric, right? And the third thing is, okay, algebraic or set theoretic. Okay, that is, look at union of tbx as n varies over natural numbers, then I claim it's all of y. Yeah, why does it follow? This is n times. Okay, why? Notice this is where we are going to use t is on to. First notice that if you start with x, that is union of n times bx, yeah, n over natural numbers. Yeah, that's very clear, because you give me any x in x, then norm of x must be, by Archimedean property, should be less than n. Therefore norm of x by n should be less than 1. Therefore n times this vector v is your x, where v is x by n. Yeah, therefore this is clear. I am going very slow because some of you would not been taught how to verify even small things. In your BS itself you should have learned all these things, but most often you would have come to MSc without knowing what are the small things you have to check. In at master's level, teachers and books assume that you know all those things. Okay, but so most often you do not know, you simply accept whatever the teacher or book says. Okay, so I want to prevent you, I want you to think ahead and learn. Okay, is that clear? Now what is tx? Since y is on to tx equal to t is on to tx equal to y, and now what is t of n bx? That we know, because of linearity it is a t of n bx. Therefore what is the union of these things? That is going to be union of this thing, right? But are you following? Right. But then t of union of n bx is same as t of x, that is equal to y, but this fellow is nothing other than union of n times tbx. So we proved the claim. Okay, these are the properties of tbx. So what are the properties you have learned? tbx is symmetric and it is convex, and union of n times tbx, okay, as n varies over natural numbers, is all of y. Okay, now what is that we wanted to claim? We wanted to claim tbx has 0 as an interior point, but you want to claim only the closure. Okay, that's an interior point of this. 0 is an interior point of the closure of tbx. Okay, where does the closeness comes? That is where the Baire's theorem comes. So let us recall Baire's theorem. Let me see, I am just recording here. What does Baire's theorem says? Suppose if xd is a complete metric space, and if you write x as union of Cn, where Cn's are closed subsets of C, so of x, then there is an n so that, okay, Cn has non-empty interior. So this is a version of Baire I want to use. Okay, people will always talk about Meager set, first category, second category. Okay, so finally you do not know where Baire's theorem is used. If you have not learned, there is a video on Baire's theorem. Please go through it. You will also see how Baire's theorem is very easy and why it's very useful. Okay, do you accept it? So what are the things I need? These Cn's must be closed, their union must be x. Now let's go back. What have we done? I know n tbx, so let me call it as this. Okay, this equal to all of y. and y is complete because of Banach space, right? But unfortunately my tbx or ntbx may not be closed, right? Because it just shows one of them will have an empty non-empty interior, right? So if I want to show there is an answer that ntbx is non-empty interior, then I'm through. We'll see why I'm through in a minute. Okay, so what do I do? So what we do is we take C to be tbx closure. This is the closure in y. Right? Then what I have is union n times C is all of y, where n varies over natural numbers. This n, if you want, put it here. Right? Now each of them, notice that C is closed because it's closed, and the map for lambda not equal to 0, x going to lambda x is a homeomorphism. Okay, it's continuous. The inverse is given by x going to 1 by lambda x. Right? Therefore, this is a homeomorphism. Therefore, the map, okay, under that map, yeah, x going to nx, okay, C, where does it go to? It goes to nc. And since the homeomorphism this is closed, this is also closed. Therefore, each nc is closed. Right? Therefore, what do I have? Therefore, by Baire, okay, there is an n in n such that n times C has non-empty interior. This immediately implies C has non-empty interior. Why? Again the same reason. Look at x going to 1 by nx. This is a homeomorphism. So if C has a non-empty interior, that open, so that means there exists some, okay, if nc has a no interior, that means there exists some bx r which is contained in nc, then 1 upon that will also be there. Yeah? Is that okay? Right. Therefore, there exists x in x, r in r, so that b x r is contained in C. What is C? This is tbx closure. Yeah? Have you understood this? Okay. Now we are going to show various things. We are going to show this tbx, namely C, tbx closure C is again convex and symmetric. Why? That's very easy, but in case you have not seen, I will go through the proof again, because I want you to learn thoroughly, not just half page proof learn by heart and produce, and you may not even understand why it works. Okay, this will also give you an idea how to read books and what are your so that you can go back and learn. Okay, that is very clear. Suppose it's convex, right? Suppose I say a y belong to tbx C. Okay, what does that mean? The first thing is, let us look at, if xd is a metric space and if xd, this is D, suppose A is a subset, and when does x belong to A closure? If you had learned metric space topology either from my videos or from my book, you know that there exists a sequence an in A so that an converges to x. Okay, x belong to A closure. Okay, I am going to use that. Now if y belong to C and C is tbx closure, that means there exists a sequence yn in tbx so that yn converges to y. Yeah, but this yn is, that means there exists a sequence xn in bx so that yn equal to txn and txn converges to y. Right? Therefore, y belong to C implies there exists a sequence xn in bx so that t of xn converges to y. Understand this well? Now we are ready to prove. Suppose there exists y1 and y and z in C, then I want to prove C is convex. That means y minus 1 minus t times y plus t times z belong to C, where 0 less than or equal to t less than or equal to 1. I have to prove this. But what I know is there is a sequence, namely, let me call it as un in bx, so that tun converges to y, and similarly vn in bx, so that tvn converges to v with z. tun converges to y and tvn converges to z, because y and c belong to the closure, right? Now let's look at, now un and vn are in bx. Bx is convex, therefore 1 minus t times un plus t times vn, that is in bx, right? Now t of that, what is the t of that? That is 1 minus t times tun plus t times tvn. But that is okay. Now remember, t is continuous. Therefore, this t of un converges to y, t of un converges to z. Therefore, this converges to 1 minus t times y plus t times z. Therefore, that's in C. You follow that? Okay. Right. So this converges. Therefore, 1 minus t times that converges to 1 minus t times y, and this converges to t times z. Therefore, okay. And what do I know? X belongs to a closure. That is, this fellow belongs to TBX closure if and only if this happens. So I am using this result. You understand that? Please, if your topology, matrix space topology is weak, please go through it, that point, and see how I am using it. We used the characterization. Let me just put a symbol here. We used this here. Okay, and similarly, this I leave it as an exercise so that you will understand. C is symmetric. Now come back. Okay, left as an exercise. Now come back. What do I know? I know there exists B. I wrote as BXR, but okay, let me, it's in an empty interior, let me write it BYR, because remember C is a subset of Y, so I should use that. Okay, yeah. So I know BYR is contain TBX closure, which is C. Right? Now this is, notice that this is symmetric. That is, therefore, if any vector z belong to that, minus z also belong to C. Therefore, what is minus of BOR? Okay, that is again easy. Let us look at BOR. Okay, if z belong to that, that is of the form z equal to y plus r times u, where u is in B of y. We had already seen, because this is nothing other than y plus r times by. Therefore, minus of that will be minus of y plus minus of r times by, right? Therefore, minus z will be minus y minus ru. But this is minus y plus r times minus u, but minus u belongs to by because by is symmetric. You follow that? Yeah. Therefore, what we found out is minus of BYR is nothing other than B of minus YR. Yeah, because this is plus R minus BY, but this is minus Y plus R times BY, but this is B of minus YR. Okay. Now you see that these are the things. If you learn, your spend a lot of time nonlinear spaces, how the open balls look like, etc., etc., these things would have been much easier, right? Therefore, what do you think I have done? Therefore, I have shown, okay, there exists, okay, B, if BOR is contained in C, implies B of minus OR is contained in C. Alright, therefore I want to claim now, this is claim, this means B0R itself is contained in C. Why? Now start with any X in B0R, then, okay, X plus RB, Y is BXR. Right? Okay, let's do that. Let me do that. See, let's look at, we know that B YR is contained in C, right? And B of minus YR is contained in C. And let X belong to this. Therefore, let's look at Y plus, maybe I will use some other notation. I don't want to use X. I'm sorry if I'm confusing. Let Y plus Z. I want to say B0 is contained in C, right? So start with any Z, I will say it is in C. Now let's look at Y plus Z. Okay, Y plus Z belong to Y plus B0R, that is equal to B of YR, but that is contained in C. Therefore Y plus Z belong to that. Similarly, minus Y plus Z also belong to B of minus YR, which is contained in C, right? Therefore Y plus Z minus Y plus Z both are in C. Now C is convex. Therefore, right, therefore if I take half of Y plus Z and plus half of minus Y plus Z, that is Z, it has to be in C. That means for every Z in B0R, okay, this is in Y, remember, this is contained in C. Therefore what I have shown, therefore, okay, there exists an R positive so that B0R in Y, this is contained in T of Bx, closure, that is C. Wow. So please pay attention, even the small things which you would never checks, okay, or never checked you earlier when you learned the basics. We did all those things. Okay, go through the proof. So what you have shown is, we wanted to show TBX has 0 as an interior point. We could not do that, but what we showed was the closure of TBX has 0 as an interior point. And what did we use for that? We used the completeness of Y, right? We used Baire's theorem, and to use Baire's theorem in Y, we needed Y to be complete. And we also used the geometry of TBX, and hence its geometry of TBX closure. Yeah, please go through the proof. Now we have to prove the next one. Okay, after a little work using completeness of X, there is an open ball around 0 in Y, which is already contained in TBX itself. That will prove open mapping theorem. Okay, we will do it in the next lecture. I hope you all enjoyed. Please go through it twice and then read my text, my book or any other book. You will see how things are easy. By the way, notice that there are the part which we did about C that could be made into a separate lemma. What is that? Let X be any nonlinear space, okay, right, so that C has the following property: C is closed, C is symmetric, and C is convex, so that union NC equal to all of X, assume X is nonlinear, sorry, Banach space. Are you following me? Let C be convex, symmetric, closed, and union NC equal to all of X, where X is a complete nonlinear space, that's a Banach space. Then what we proved that C has an open ball around 0 contained in C. That's a proof. That's a separate lemma. Please understand that. Okay, I don't want to write it, but if you want me to write, I will say that. Okay, this is the lemma we have proved. did I make so this is a lemma. Let X be a Banach space and C in X be convex, close, symmetric, and union in C equal to X. Then there exists R positive such that R times Bx is contained in C. This all we proved. Okay. Go back and see how you got it and try to write this lemma as is. Okay, instead of TBX etc. Now try to use it directly. You will love that. This will also be a good exercise to make you understand the proof. Okay, we will meet again.